All right, so ladies and gentlemen, this is part 2 of the video for rotational energy and work. So this practice problem, it's 2 parts, and this is kind of a great problem for highlighting how rotational energy can affect the motion of something. All right, so what I have here is I have a setup, and I have a cylinder, all right, and it's got a mass of 2m. And what I've done is instead of setting it up so the cylinder can roll, I have laid it basically on its side so that it just can slide, all right? So I have a cylinder of mass 2m. It's sitting on its side on a low friction surface. So you can assume its friction is pretty much negligible. And it's at a height h. And we're going to let it start sliding until it reaches the bottom. And then after it does that, it's going to slide across this rough surface for some distance before it finally stops. All right. So the first thing I want us to do is I just want to calculate how fast is it moving at the bottom. All right. And in fact, I want you to do that if you don't mind. And actually, I want you to do both these questions. All right, I'm confident at this point we know what we're doing. So I want you to first use only variables, solve for how fast this object is moving at the bottom, and then I want you to calculate how far does it slide. All right, and my suggestion is to use work done by friction to calculate this. All right, so pause the video here. When you're done, come back. We'll talk about what the answers are to both of them. All right, so hopefully, ladies and gentlemen, you had a chance to work through these 2 practice problems. All right, these 2 little parts. This is just a review on energy. So it all goes back to what we know about the rules of energy. We're going to use the law of conservation to figure out how fast it's moving at the bottom. So it starts with just potential energy because we know it is not moving anywhere at the moment. So it only starts with UGI. And at the bottom of the hill, it no longer has any sort of potential energy. It's all been turned into kinetic, so it's final kinetic energy. Now, because it is sliding, it's not rotating at all right? So it only has linear kinetic energy. So when we write our formulas, we start with potential. It's going to be 2m, because remember, potential is just mgh, the mass times the gravity field times the height. So 2m times g times h is going to equal the linear kinetic energy, 1/2, times the mass of the object, 2m, times the linear velocity squared. All right, and of course we can do a little simplification here. The masses cancel out as they normally do, so we're left with basically v squared equals 2 times gh, because I moved the 1/2 over. All right, and then of course when you use some square root, you should get that basically the predicted linear velocity is going to be just the square root of 2gh. All right, and this is a problem we've done plenty of times. This is a great practice problem just to kind of get used to, once again, the idea of how energy is transformed. One great way to make this a bit more difficult is to make the incline, my apologies, the word just slipped my mind. Make it have friction, practice that, or have it, you maybe slide it up the ramp, let it slide down. This is a great way to practice it. All right. Now, the second question, how far does it travel past the bottom of the hill before it stops? I suggested using maybe work to solve that. Remember, work is force times distance. So, times cosine of theta, but we don't really have to worry about that. Looking at this particular question, all right, if we rewrite the law of conservation of energy again, this time we're at the bottom of the hill, so we say our starting energy is just kinetic. We want all of it turned into work when all is said and done, work by friction specifically. All right, so to do that, we first start with what we know the starting kinetic energy is. Remember, once again, 1/2 mv, 1/2 2m v squared, 2m v squared. All right. Now we know the velocity from previously. We just found it, so actually we can plug in that v. We can plug it into our formula. So this v squared is just going to be the square root of 2gh squared. So that just turns into basically, we've got now 1/2 times 2m times 2gh. All right. And what this does, ladies and gentlemen, what we're doing is this tells us this is the amount of energy that we started with. All right. And wouldn't you know it, just to kind of tie it back to what we talked about before, amazingly enough, that is exactly equal to the amount of starting potential energy we would have. So fascinating. All right. Now, we know that we want all of this to eventually be taken away by friction. All right. So that means we need to use the work formula, which is just equal to force times the distance, all right? So in this case, it's going to be the force of friction times the distance. It slides, basically. Now, we're looking for that distance, and it seems at first like we can't really do anything else. But remember, if we have a formula that we can replace something with, we do that and see if we can simplify. So in this case, I know that the force of friction is just equal to the coefficient of friction times the normal force. All right, so I'm going to put in my stickiness there. Times the normal force. I'm going to do a little simplification because we should be very confident at this point that when this object is sliding across the floor, the normal force and the gravitational force are actually going to be the same because it is not falling through the floor. So instead of doing mu times the normal force, I'm going to go mu times Fg. And oh my gosh, Fg is just m times g. Remember that, okay? And it's 2m because it's the mass of the block, or the cylinder, excuse me. All right, so I know I just did like 4 steps in there. All we've done right now is just write out the formula for force of friction, okay? Then we're going to multiply that by some distance x that we do not know. But wouldn't you know it, ladies and gentlemen, we actually can simplify this much more now because we're pretty dang close. Because if we look at it, we'll see that the starting energy it has is 2 mgh. Over here, the amount of work done is going to be 2 mg times the coefficient of friction times some distance x we don't know. So we can cancel out the 2 mg's on both sides. So we're left, when we simplify a little bit more, we're left with basically that the distance is going to be equal. We have the height it started at is just equal to mu times the distance it has to slide. And wouldn't you know it, we can move that around real quick so you actually get that the distance that it goes is just equal to h divided by mu. All right. Now, I know I did a ton of fast math right there. What really matters is that we can once again see the idea, ladies and gentlemen, that work can take away energy. And we can use the same rules that we did to figure out how fast it's sliding at the bottom to figure out how far it has to go before it stops. And you could have very easily also done this using net force and kinematics if you wanted to. It would have been a totally acceptable way to do this as well. It's really up to you. All right. Now, here's a much more interesting part. I take the cylinder and I pick it up and I move it back to where it started. So it's now at a height of h again. But this time I have arranged it so now it's on its edge so it can actually roll. All right. Now, once again, it's on a low friction surface, so it won't experience any sort of frictional slowdown on the hill, but once it gets to the bottom, it will. And I want you actually to answer the following question without any calculations. Explain why the speed of the cylinder will actually be less when it rolls down the hill compared to when it was simply sliding. All right, so pause this video and I want you to answer that question. Why do we think it actually will be moving slower, have a slower linear velocity than it would previously? All right, so hopefully if you had a chance to kind of look through it, if we think about the energy transformations that are happening, originally it was all potential to all linear kinetic. But now there are 2 different kinetic energies that the starting energy is being transformed into. So the linear kinetic energy is actually less. So because of that, this object will not actually be moving as quickly to the right. Its linear velocity will be less. All right, so without any calculations, we can just say 2 types of kinetic energy now. Pulling 2 times kinetic energy using the starting potential. However you want to word it is up to you. All right. Now, we want to figure out again how fast is it moving at the bottom. This time, however, we're going to have to work a little bit differently. So, of course, we do the same thing we did before. We write out the law of conservation of energy. Same thing as before. It only starts with potential. Nothing's different about that. But now, at the very bottom, it now has 2 types of kinetic energy. So it has linear kinetic energy, and it has rotational kinetic energy. All right. Now, if we want to solve this using some formulas, we're going to have to do a little bit of work. So we know, once again, we know this, UGI, that's going to be MGH, 2 MGH, excuse me. Once again, we know that KF is 1/2 times the mass, 2m, times v squared. And then we use this new formula for rotational kinetic energy. And what that is we say, all right, this is 1/2 times the moment of inertia of a cylinder, which unfortunately I did not give you. I will give it to you a little bit later, but it's 1/2 m the radius squared, okay, times the rotational velocity, and we use it as a w, squared. Now, of course, right away, I know this looks really ugly, but I promise this isn't that big a deal. So what we're going to say is we're going to say basically that the cylinder has a radius r. This has a mass of 2m, so when you calculate the moment of inertia, you just use 2m, okay? Now, if we simplify this, we're left with a little bit of an issue, okay? And that issue is that we will now have two different variables. So we need to basically, we're looking for how fast it's going. We're looking for linear velocity. So we need to really get rid of that rotational velocity, okay? Now, what that means, if I simplify this real quick, just to make it a little bit easier to see, this is mv squared plus, what I have to do is I have to basically use a relationship that we have between linear velocity and angular velocity. All right, and if you're wondering what I'm doing right now as I'm talking, I'm just simplifying this. So the 1/2 times the 2m, that simplifies r squared times omega squared. All right, now what we're going to do is we're going to think back to what we talked about when we kind of introduced the idea of linear and rotational velocity. And what we're going to think back to is the idea that linear velocity is actually just equal to the rotational velocity, it's the spinning velocity, times basically the radius of the circle, or how far away you are from the turning point. Well, in this case, wouldn't you know it, we're looking at basically how fast it's going on the edge, all right, for its linear velocity, which means that we can use omega times r, and we can actually relate back to linear velocity. Now, why that's useful for us is because if we look at this formula, we have m times r squared times omega squared. And if we look at these two terms together, that's actually the same thing as saying v squared. So in fact, we can simplify this a little bit, and it now turns into just mv squared plus 1/2 the mass times v squared. All right. Now, what we've done is just kind of incorporate the fact that this has rotational energy. So because of that, once we do this, we can just add it all together and solve for it. So all the m's go away. We just do a little bit of math. So you get, it's like 2gh equals, and I'm just doing some quick math because I'm slowly running out of time here. 2mgh equals 3/2 v squared. Do a little bit of math, and you should get that now the velocity is going to be the square root of 4gh divided by 3. All right? And what that is that's less than it was originally, which is exactly what we expected. So what we've done is just prove that this linear velocity is actually less now because we're allowing this thing to roll. Because rolling means that you have not only linear motion, because it's moving forward, it also now has rotational motion, so you have to take both into account. All right? So last piece is, ladies and gentlemen, before we're done, is I want you to just answer this particular question. So we're going to let it go across the ground, which means, once again, it's going to eventually slow down to a stop. And I want to know, do we think the amount of work done by friction to stop the cylinder will be any different than it was in the original scenario? All right, so take a sec, just think about that, and then we'll answer it. All right. Hopefully, thinking about all the energy transformations, you kind of thought about the idea that the work is just taking away whatever the starting energy was. And the starting energy in this situation was no different than it was in the previous situation when it was kind of laying on its side. All right. So in fact, the amount of work will be exactly the same because the starting potential energy was exactly the same. All right. So once again, ladies and gentlemen, we're just thinking about the idea that the rules of energy still apply to things that are rotating. It's no different than it was for linear motion. We're just including an extra term now. And when things are rolling, it means not only are they moving forward with linear motion, but they're also moving with rotational motion as well. All right. So that being said, ladies and gentlemen, have a great rest of the day, and I'll talk to you later.